Inequalities. Now we'll have a couple videos on inequalities. So to start, I'll say, so far in algebra, we have focused a great deal on equations and on what has to be true to make things equal. And that's an important topic, but sometimes in math, and even in real life, we need to find out whether something is bigger, smaller, or just not equal to something else. And this is the basis of the idea of inequalities. The test uses 5 inequality symbols that you need to know and understand. These are the 5 inequality symbols. So let's talk about these. First of all, the less than and greater than symbols. A is less than B, C is greater than D. First thing I'll say is that it might be helpful to remember these by thinking about that as, say, the jaws of something like a crocodile. In other words, it's open toward the bigger thing. The crocodile's hungry, so it wants to eat the bigger thing. That's a wonderful little trick that they teach little kids, but it can be very helpful actually if you have any confusion between these two symbols. Also notice that these first two have an inverse relationship. In other words, if A is less than B, that necessarily means that B is greater than A. So we can just swap the order around and reverse the direction in which the inequality is pointing. Now, the less than or greater than or equal to symbols. So A is less than or equal to B. C is greater than or equal to D. And so these are interesting because it leaves open the possibility that the two are equal or that one is bigger than the other. And again, these are also inverses. If A is less than or equal to B, that necessarily means that B is greater than or equal to A. And finally, A is unequal to B. So either one could be greater or less. All we know is that they don't have the same value. So all 5 of these are used in the specifications for problems. So at the beginning of a problem, it might say something like, if x is greater than or equal to 10, or x is unequal to 5, or blah, blah, and then they'll talk about the rest of the problem. So that is just a condition they specify to make the problem work. And so any of these 5 symbols can appear in that specification. Now the first thing I'll say about these is, with inequalities, it is very important not to be naive about numbers. What do I mean by that, naive about numbers? Think about it this way. For example, the specification x is less than 5 does not mean the same thing as x is less than or equal to 4. And this is very typical. This is a very typical mistake pattern. And what's going on here, people are thinking that x can only be a number that they can count on their own fingers. Or in other words, people are only thinking about positive integers. And so this is the type of confusion that arises when people get caught in that, when they're thinking about all numbers are just positive integers. All numbers are numbers I can count on my fingers. In fact, when you see the word number, or just when you see an x, and all it's talking about is an x, and they don't specify anything else, you have to think of all possible numbers. This could be positive, negative, or 0. It could be integers, fractions, and decimals. It can be any kind of number on the number line. The whole number line is open when we just have the word number or when we just see the variable x. Now think about this. Think of all the values that would satisfy the inequality x is less than 5 and that would not satisfy the inequality x is less than or equal to 4. Now, of course, there are no integers in that range, but there are many other numbers. So examples include all the decimals between 4 and 5. All those are things that legitimately are less than 5, but they are not less than or equal to 4. And notice that last one in particular, 4 followed by a bunch of 9s after the decimal point. So that's a very interesting one. Of course, that number is less than 5, and you might think, well, gee, it's awfully close to 5, and yes, it is close to 5. Here's the mind-blowing part, though. How many numbers are greater than that last number, but still less than 5? And the answer, the mind-blowing answer, is infinity, between any 2 points on the number line. No matter how close those 2 points are, between those 2 points, there's an absolute infinity of numbers. And so that means if you leave out the numbers between 4 and 5, you're leaving out an infinity of numbers. You're leaving out more numbers than there are stars in the universe. So that is the magnitude of that error. So it's very important to be discerning when you read inequalities. It's very important not to fall into that trap at any point of thinking that all possible numbers are just the numbers that you can count on your fingers. You will have to use the first 4 inequality symbols in problem solving. The test will not have you work with the unequal sign in problems. So when you actually have to do work for yourself, you could see greater than or less than or greater than or equal to or less than or equal to, but work that you have to do with yourself, you will not just see the unequal sign. The unequal sign might appear in the specification of problems. In that sense, you'll need to know it, but you will not have to work with it. An algebraic statement involving one of these 4 symbols is known as an inequality. All of these are inequalities. With equations, we can do almost anything. We can do almost anything to one side as long as we do the same thing to the other side and the 2 sides remain equal. Equations are very easy to handle that way. What operations can we perform to both sides of inequality that preserve the statement of the inequality? So in other words, we have an inequality, say greater than or less than, pointing in a certain direction. We want to do the same thing to both sides, and we want to understand, are those things still greater than or less than? We have to understand that. So, first of all, we can always add the same thing to both sides or subtract the same thing from both sides, and the inequality remains the same. So addition and subtraction work exactly the same way with inequalities as they work with equations. So that much is easy. So for example, if I have the inequality x plus 7 is greater than 2, and I want to get x by itself, I subtract 7 from both sides, and of course I get x is greater than negative 5. And so that is the solution range for x. Addition and subtraction work the same way with equations as they do with inequalities. With multiplication and division, things are a little trickier with inequalities. We can still multiply or divide both sides by any positive number. That will preserve the inequality. So if we know what we're multiplying by is a positive, if we're guaranteed of that, then multiplying and dividing with inequalities is exactly the same as equations. You can just do the same thing to both sides. What's trickier is that multiplication or division by a negative number reverses the order of the inequalities. So for example, if I have negative x is greater than 3, well, if I want to get x by itself, I have to multiply by negative 1. And of course, I'll multiply both sides by negative 1. But that has the effect of changing the direction in which the inequality points. So the negative x becomes a positive x, the 3 becomes a negative 3, and that greater than sign has to become a less than sign. And so the final statement is x is less than negative 3. One easy way to see why this is to think about what happens with ordinary numbers. So take the variables out entirely, and let's just think of ordinary numbers. So here are 2 valid, legitimate, true inequalities. It is true that 7 is greater than 3. It is true that 5 is greater than negative 2. Well, let's multiply everything by negative signs. It is also true that negative 3 is greater than negative 7. Negative 3 is to the right of negative 7 on the number line. And of course, negative 5 is less than positive 2. So in other words, in order to maintain true statements, when we multiply by negative 1, we have to reverse the direction of the inequality. So, here's a practice problem. Pause the video and then we'll talk about this. So we want to get x by itself, so much in the same way as with equations. First, we want to collect all the x's on one side, so I'm going to subtract 2x from both sides. Then I get 5x minus 2x is 3x. Now I'm going to subtract 7 from both sides. Now I'm going to divide by positive 3 because I'm dividing by a positive number. That's just like an equation. Everything else is just going to stay the same. I can just do the division on both sides, and I get x is less than -3. Now, sometimes they'll have the solution written in this algebraic form. Sometimes they'll write it on a number line. And of course, x is less than -3 is written on a number line like this. Notice there is a circle at the 3, an open circle, indicating that 3 is not a legitimate value. So -3 is not one of the values in this solution. -4, -5, -6, those are legitimate values. Those are things that are less than -3. But of course, -3 itself is not less than -3. So -3 is not included. So the end point is not included in that region. And the purple is the allowable region. Here's another practice problem. Pause the video and then we'll talk about this. Notice, first of all, that x cannot equal 0. If we made x equal 0, then we'd be dividing by 0, and we wouldn't have a sensible expression. Notice also that x has to be positive, because the fraction on the right is a positive number, and so the only way the fraction on the left is going to be greater than it, or equal to it, is if it's also positive. There's no way that it could be negative. No negative can be greater than a positive. So x absolutely has to be positive. Because all numbers are positive, we can simply cross-multiply. So just plain old cross-multiplying, we cross-multiply, and we get that 6 is greater than or equal to x. Well, if we combine all these conditions together, we see that x has to be greater than 0 and less than or equal to 6. And so this would be the allowable range. Notice that there is an open circle at 0 because that's not included, and there's a solid dot at 6. So the left endpoint is not included, the right endpoint is included in the solution range. Here's another practice problem. Pause the video and then we'll talk about this. This is tricky because this is a series of inequalities, but we do this exactly the same way as we do anything else. First of all, we can just subtract 5 from all 3 of them, and that's how we get -4 minus 5 is -9. We cancel the 5 in the middle, and then 17 minus 5 is 12. So we have subtracted 5. Now we're going to divide by -3 to get the x by itself. And of course, if we divide by a negative, it means both those inequality signs have to flip around. So they flip around like this, and that we get x is between. So x is greater than or equal to -4 and less than 3. So this is the solution range. And notice that we include -4. We have a solid dot there. We have an open circle at 3 because that's not included. So the left endpoint is included in the solution. The right endpoint is not included in the solution. And just to be clear, we could have any decimal up to 3. We could have 2.9, 2.99, 2.9999999. We could have any decimal as close as we want to 3, and that would still be in the solution. We just can't equal 3. In summary, we can add or subtract with inequalities exactly as you do with equations. We can multiply and divide inequalities by positive numbers. If we multiply or divide an inequality by a negative number, this reverses the direction of the inequality. In this video, we'll talk about a few more ideas related to inequalities. First of all, suppose that more than one inequality is given in a problem. What are we allowed to do with 2 separate inequalities? So, combining inequalities. If we have 2 equations, first of all, a equals b and b equals c, we can certainly combine them to get a equals c. Technically, that's called the transitive property of equality. Much in the same way, if we know that r is less than s and s is less than t, we can deduce that r is less than s is less than t, and therefore r is less than t. So that is also a transitive property. Notice that in order for the combination to work, the common term s has to be greater than one term and less than the other term. And that's very, very important. If the same term is greater than both other terms or less than both other terms, we cannot draw any conclusion. If C is less than F and D is also less than F, we know that C and D are both less than F, but we don't know how they compare to each other. So for example, if F is 100, then C and D are both numbers less than 100, but there's nothing telling us which one is bigger than the other. The second issue, adding inequalities. Recall that we're allowed to add or subtract any two equations. Turns out equations are very easy in this regard. With inequalities, we need to be more careful. Suppose we have two inequalities, A is less than B and C is less than D. What sorts of addition and subtraction are allowed? First of all, we can add inequalities with the same direction. In other words, with the inequality pointing in the same direction. So if A is greater than B and C is greater than D, then we can just add them together. A plus C has to be greater than B plus D. And that sort of makes sense, that if we add the two big things, it's going to be greater than the sum of the two small things. For example, 5 is greater than 2 and 11 is greater than 8. Those are two true inequalities. We can add them when the directions are the same. So when we add, of course, we get another true statement, 16 is greater than 10. We do not necessarily get anything sensible if we add inequalities that do not have the same direction. So for example, these two inequalities, now we flip one around so they have opposite direction. Adding these, well, what happens, we get 13 on both sides, and in fact that's not an inequality at all, that's in fact an equation. And if we pick different initial values, we could produce a sum that would either be greater than, less than, or equal to. And so it means that there's no general rule. When you start adding inequalities where the sign is pointing in opposite directions, basically you get mathematical nonsense. There's no way to predict what you're going to get. So in this case, for subtracting inequalities, we cannot subtract inequalities with the same direction. So here are a bunch of inequalities. These are valid inequalities, all lined up so the inequalities in the same direction. Notice that if we subtract, well, in different cases, we could get a less than sign, an equal sign, or a greater than sign. If we subtract inequalities with the same direction, we could get any of those signs. So again, it's pure mathematical nonsense. If you subtract two inequalities with the same direction, there's no way to predict what kind of relationship will result. But in this case, we can subtract inequalities that have opposite directions. So if A is greater than B and C is greater than D, we have nowhere to compare the size of A minus C to the size of B minus D. If we do big minus big and small minus small, well, it's hard to say how that's going to compare. But we can turn the latter around, make it D minus C, and then we can subtract. A minus D is greater than B minus C. So in other words, big minus small is always going to be greater than small minus big. So this works. Think about this statement. If A is greater than B and D is less than C, then A minus D is greater than B minus C. Let's do a numerical example. Suppose A equals 20, B equals 15, C equals 12, and D equals 10. Clearly, 20 is greater than 15. Clearly, 10 is less than 12. And when we subtract, we get 10 is greater than 3. So notice that the resultant inequality follows the direction of the initial inequality, the one from which we subtract. So that sets the tone. That first one from which we subtract from that something in the opposite direction, and the result, the difference, will be the same as the original. There are no rules for multiplication and division of inequalities. Again, it always results in mathematical nonsense. You cannot do it. You might think that if A were greater than B and C were greater than D, it would always lead to A times C is greater than B times D. Why wouldn't it be that big times big is always greater than small times small? If we were guaranteed that all the numbers are positive, then that would work, but consider this example. Negative 10 is clearly less than positive 2, and negative 8 is clearly less than positive 3. But if we multiply, we get negative 8 times negative 10, and negative times negative gives us positive 80, which is greater than 6. 2 times 3, which is 6. So this is an example where multiplying the two quote-unquote smaller numbers, the negative numbers, gives a very positive, a very large product. And so that's why there are no rules whatsoever for multiplication and division of inequalities. It is definitely true that any positive number is greater than any negative number. Now that might be an obvious statement, but this can be a useful shortcut in certain circumstances. If we know that a number is negative, we don't need to calculate its exact value. We know for a fact that just by fact that it's negative, it is always less than any positive number. Also, keep in mind that adding any positive number always makes a number bigger. So, for example, x plus 10 has to be bigger than x. And in fact, any positive number could even be a fraction. X plus 2/5 has to be greater than x. Much in the same way, subtracting any positive or adding any negative makes a number smaller, always. So x has to be greater than x minus 3. Subtracting 3 necessarily makes anything smaller. So here's a practice problem. Pause the video and then we'll talk about this. So this is a very test-like problem, and in particular, it's a test-like problem because it's designed with some traps that would punish people who think very naively about numbers, who think that all numbers are the numbers that they can count on their fingers. They forget about other kinds of numbers. So first of all, that first statement, that is legitimately true. That if we add 2, doesn't matter whether the number is positive or negative, a fraction, doesn't matter. If we add 2, we make it bigger. So that is always greater than x. And because 1 has to be included in the answer, we can eliminate answer D, because that one doesn't include 1. Okay, what about 2x? Is 2x always greater than x? Now, if you're thinking about positive numbers, this is where you could run into a problem, because of course if you double any positive number, it gets bigger. 6 is bigger than 3, 20 is bigger than 10, that sort of thing. The problem is when we get to negative numbers. If I have negative 10 and double that, that's negative 20. Negative 10 is greater than negative 20. One way to think about that, which is better? Would you rather be $10 in debt or $20 in debt? You're much better off financially if you're $10 in debt rather than $20 in debt. And so that's one way to think about it. Negative 10 is definitely greater than negative 20. So with negative numbers, that just doesn't work. So 2 is not always true. And so that means we can eliminate any of the answers that include 2. And so now we're just down to A and C. Finally, x squared. Now this is particularly tricky because, of course, with most positive numbers, you square it and it gets bigger. And with negative numbers, you square a negative, it becomes positive. So, of course, that's bigger also because any positive is bigger than a negative. So it might look like, gee, we're all set. Well, first of all, notice that there are a couple numbers, if we square them, like 1 and 0. If we square 1, we get 1. If we square 0, we get 0. Well, that's not an inequality. That's an equality. 1 squared equals 1. It's not greater than 1. And also, think about the decimals between 1 and 0. If we square 1/2, we get 1/4. And 1/4 is less than 1/2. When we square fractions, they get smaller. And so that means that this final one is not always true. And so we can eliminate the other answers, and just by process of elimination, the only one that works is answer choice A. In summary, we can combine inequalities if the common term is less than 1 and greater than the other. We can combine everything in the same direction. So A is less than B, B is less than C. We can combine that into A is less than B less than C, which tells us directly that A is less than C. We can add inequalities in the same direction. We can subtract inequalities in opposite directions. There's no general rule for multiplication or division of inequalities. Any positive number is greater than any negative number. And again, that is a very handy shortcut under many circumstances. And finally, adding a positive number makes a number greater. Subtracting a positive makes it less. Now we can talk about absolute value inequalities. First thing I'll say, if you haven't seen the introductory lesson on absolute value in the lesson Positive and Negative Numbers 2 in the Arithmetic and Fractions module, I strongly suggest that you watch that lesson first before you watch this one, because that's where we explain this basic understanding of absolute value. So if you're confused with absolute value as distance, why are we talking about absolute value and distance? It's explained in that lesson. I'll assume that you have watched that lesson already. So recall the distance definition of absolute value. The distance of x from 0 is absolute value of 0. We take the absolute value of any number in the number line, we get its distance from 0, distance from the origin. If we want the distance from positive 5, well, then we have to subtract. Subtraction is the basic way that we find distance. We subtract and take the absolute value. So absolute value of x minus 5. And so if I plug in x equals 8, then I get x minus 8 minus 5, absolute value of 3 is 3. And so 8 is 3 away from 5. And if I plug in 2, then I get 2 minus 5, negative 3, absolute value is 3. 2 is also a distance of 3 from 5. Now suppose I want the distance from negative 3. Well, again, we would subtract. But here's the tricky thing. When I subtract a negative, it becomes positive. And so that's confusing to some people. They see this positive and they say, well, why is it that we get a positive when it's a negative we're concerned with? Well, it's because we're subtracting. And when we subtract x equals negative 3, we get x equals plus 3. And one way to think about this is with ordinary numbers. Suppose x equals negative 4. Well, how far is negative 3 from negative 4? Well, it's right next to it on the number line. It's 1 away. And if we plug into the formula, we get absolute value of negative 4 plus 3, absolute value of negative 1 equals 1. So the point negative 4 is a distance of 1 from negative 3. But if we plug in positive 4, well, then we get 4 plus 3, absolute value of 7 is 7. And that makes sense because negative 3 is down here and positive 4 is up here. And so we'd have to go, if we started at 4, we'd have to go a distance of 4 to 0 and then another 3 to get to negative 3. So that would be a distance of 7. So even though this is anti-intuitive, the formula actually works when you plug in numbers. So in general, if we want the distance from a positive value of p, then the formula would be x minus p. And if we want a distance from negative p, then it would be the absolute value of x plus p. And again, some people are confused. How come the signs swap here? And you have to remember that it's a subtraction. Here we're subtracting a positive. Here we're subtracting a negative. And subtracting a negative results in addition. This way of thinking about absolute value in terms of distance is enormously helpful in understanding inequalities that involve absolute value. Here's a practice question. Express absolute value of x minus 7 is less than 3 as an ordinary inequality. Pause the video and think about this for a moment. Okay, so what we're saying is that if we start from 7 on the number line, we can go up to and including a distance of 3 in either direction. So if we went down 3, we'd get to 4. If we went up 3, we'd get to 10. Those are the two endpoints, and those are included because we have a less than or equal to sign. So it includes the endpoints. And so it would be everything from 4 to 10. everything is allowed from 4 up to 10. So that would be 4 less than or equal to x less than or equal to 10. So that is an expression of this absolute value inequality as an ordinary inequality. Those two express exactly the same information. Express this ordinary inequality, 5 is less than x is less than 17, as an absolute value inequality. So now going the other way. Well, let's talk this through. This is a bit tricky because notice that the absolute value inequalities are all about some center point and how far away you can be from that center point. And so the first thing we need to do if we're going to turn it into an absolute value inequality is find that center point. And the way we do that is we take the average. So what's the average or the midpoint of 5 and 17? We'll add them up, divide by 2, we get 22 over 2 or 11. And notice that 5 and 17 are both a distance of 6 from 11. In other words, if we start at 11, go up 6, we get to 17. We go down 6, we get to 5. And so we'd write this as the distance from 11 is less than 6. In other words, we could go all the way up approaching 17, but we can't actually get to 17 because this is a less than sign, not less than or equal to. And so that's why we have a less than sign here, not less than or equal to. Again, this ordinary inequality and this absolute value inequality state the same information. Here's a practice question. Pause the video and then we'll talk about this. Okay, here we have a graphical representation of an inequality. And a few things to notice. We have open circles at the endpoint. So open circles, that's how we would say that the endpoints are not included. So we're including everything down to 20, but not 20 itself. So in other words, if we were going to write this in terms of numbers, we would say 20 less than x is less than 90. So in other words, 20 and 90 are not included. That's why we have open circles. If they were closed circles, these would be less than and equal to signs. So the very first thing we need to do to turn this into an absolute value inequality is to find the midpoint. The middle of the region is the average of those two endpoints, 20 and 90. When we add them, 20 plus 90 is 110. Divide by 2, we get 55. So 55 is the middle. And notice that if we start at 55, right here, the middle, then how much are we going up or down? Well, we're going 35 up or down because if we go up 35, we get to 90. If we go down 35, we get to 20. So in other words, what we're saying is starting from 55, we can go up to, but not including, a distance of 35. So that is absolute value of x minus 55. The distance from 55 is less than, but not equal to, 35. And so this is the correct answer. We remember this, go back to the answer choices, and choose answer choice D. Express the region -3 less than or equal to x less than or equal to 11 as an absolute value inequality. We'll notice a few things. First of all, notice that the endpoints are now included because we have less than or equal to. We still need to find the midpoint. And so we'll take the average, we'll add those two up. So -3 plus 11, positive 11 is positive 8. Divided by 2 is positive 4. So 4 is the middle. If we start from 4, we go up 7 to get to 11, or we go down 7 to get to -3. So the distance from 4 is going to be less than or equal to 7. The distance from 4 is less than or equal to 7. Go back to the answers and choose answer choice C. We demonstrated how the distance understanding of the absolute value makes inequalities involving absolute values very easy to solve. Simplifying with substitutions. In this video, we discuss a sophisticated trick for simplifying some of the hardest algebra problems on the test. So this is relatively advanced material, so just be aware this is not something you're going to need on easier problems. You're only going to need this on some of the most advanced problems on the test. This trick involves some right brain pattern matching. So the left brain, just a quick reminder, the left brain, that's the part of the brain that's really good at following rules and procedures and recipe. The right brain, that's the part that is much better at intuition and matching patterns. And so that can be harder to train, and so sometimes it's hard to see these right brain things until they're pointed out. So here's a practice problem. Pause the video and think about this practice problem for a minute. Think about how you would go about solving this. Okay, well obviously we have something that is quadratic-like, so we definitely want to subtract the 24 and get everything equal to 0. Now we could use FOIL to multiply out 2x minus 1 squared, then we get a bunch of different terms, then we distribute the 5 in the other term, we'd collect all the like terms, we'd wind up with a horribly large number of terms. It would take many steps to simplify that, and then we'd still have a quadratic we'd have to factor. Well, think about it this way. Instead, since that same thing appears twice, what happens if we just let u equal 2x minus 1? So everywhere where there's a 2x minus 1, we're just going to replace that with a u. Well, then we get this remarkably simple equation, u squared plus 5u minus 24 equals 0. Well, that's something we can solve. We can factor that and find both values of u. All right, now we have to be very careful. Those are not the answers yet. Those are the values of u. Now what do we do with this once we have these values of u? Well, now what we're going to do is we're going to set those, everything that equals u, that's going to equal 2x minus 1. So we use these values of u to solve for x. So if u equals negative 8, that means negative 8 equals 2x minus 1. And similarly with the other one, solve each one of those for x, we get x equals negative 7 halves, or x equals 2. And those are the solutions. Here's another practice problem. Pause the video and think about how you would solve this. Okay, much in the same way, let u equal x squared plus 1, because that's the thing that appears twice. Then that entire equation becomes u squared minus 15u plus 50 equals 0. Very easy to factor, u minus 5, u minus 10. And this means that u equals 5 or u equals 10. Well, now that we have these values of u, we'll use these to solve for x. So it means x squared plus 1 equals 5, or x squared plus 1 equals 10. Subtract 1 in both equations. Take the square root, keeping in mind that we need both the positive and the negative. So x is positive or negative 2, or x is positive or negative 3. So it turns out that original equation is actually an equation that has 4 different solutions. Finally, a very different kind of problem. Pause the video and then we'll talk about this. All right, one way to go about this, break this into stages. Let a equal that entire denominator. So we're just going to simplify this. So all we're dealing with is 3 divided by a equals 15. Well, we can multiply by a, divide by 15, and that simplifies to 1/5. So a equals 1/5. That whole denominator equals 1/5. All right, well now we have that piece. Now, let b equal that ugly fraction thing. Then, of course, the denominator is just 1 minus that fraction thing. A equals 1 minus b. Plug in the value we have for a. We can solve for b, so b equals 4/5. So this means that 8 over 7 plus k equals 4/5. Well, now what I'm going to do with this, first of all, remember with proportions, we can cancel a common factor in the two numerators. So I'm going to cancel a factor of 4 in the two numerators, divide both sides by 4. Now I can just cross multiply. I get 7k equals 10, subtract 7, I get k equals 3, and that is the solution. So that's a relatively efficient way to go through that problem. In summary, if one expression is repeated in an equation, we can choose a single variable, often we use u, for that expression, solve for its value, the value of u, and then use that to solve for the original variable. If an algebraic expression has multiple parts, such as a compound fraction, we can solve for the numerical values part by part.